So now we are just learning to draw FBD, and later we'll see how we are going to use this FBD. Suppose there is a body of mass m and this is a string, and this is hung from ceiling. The whole system is at equilibrium and these strings are symmetrical with respect to the whole system. That means this angle theta is same as this angle theta. Now you have been asked to draw the FBD of this mass m. To draw the FBD of mass m, you have to take into account all the forces acting on mass m. One obvious force is mg, force due to earth pulling it downward. Now this has to be balanced by the tension in the string, as one of the forces we studied before. This has to be balanced by the string force. There will be some tension in the string and that tension will act along the string. So there is a tension T and there is another tension T, making angle theta with vertical. Again, as you can see, this vector I have drawn a little smaller than this vector, but this is just an indicative diagram. You don't have to take these things very stringently that the length of the both tension has to be the same. You have drawn the proper direction and with almost same length, that is good enough. This FBD is good enough. There's nothing wrong in this. Okay, so this is the FBD of the block, and the tension when we look at the equilibrium condition that we're going to study a little while later, we're going to find out how much will be the tension in the string and those things. But for now, this is the FBD of the block, showing all the three forces acting on the block. Okay, this is a system. Two spheres are kept on a surface and there's a plank kept on symmetrically with respect to both the spheres. Now you have to draw the FBD of the plank. Now if you have not started yet, now you should take a piece of paper and pen and do it along with me. If you're just sitting and watching, you're losing. You're not learning anything. So we're going to draw the FBD of this plank. FBD will include all the forces acting on the plank. That's it. So we have to isolate the plank from rest of the system and look at the forces. Gravity act on the center of the mass. This is how mg would be acting. Suppose this is m is the mass of the plank. So gravity is acting downward, and there are two contacts you can see, and there will be some normal reaction on both the contacts, and by the argument of symmetry we can understand both would be the same. Later on we'll see the condition why both will be the same, but for now you can call this normal reaction as N1 and this normal reaction as N2. So at the point of contact, you show normal reaction like N1, and here there's another normal reaction N2. And from this condition of equilibrium, we understand very well that the forces in the vertical direction should be the same. N1 plus N2 should be equal to mg. Only then the forces would be balanced and the plank would be stationary. Okay, now draw the FBD of one of the sphere. For the sphere, the force one, of course mg, let's call it as m1g, would be acting downward. There are two contacts. If we take the contact of surface, there are two contacts for the sphere. One is from the surface, another is from the plank. So there will be some normal reaction from the plank, and see that normal reaction will be downward on the sphere because the mass is kept above it. So mass is pressing it downward, and from the reaction pair you can see the normal reaction on the plank is upward. So the normal reaction on the sphere will be downward, and you can have a very good feel as to why it will be downward, because plank is above the sphere and it is pressing the sphere downward. So there will be some normal reaction at this contact point acting downward. The magnitude of these two will be the same, their action-reaction pair. And there will be another now this normal reaction and this m1g, that means the Planck is pressing it downward and the earth is also pulling it downward, and both the forces should be balanced from the normal reaction from the surface, so that there will be third normal reaction from the surface acting upward. Let's call it as N2. Now from the static equilibrium condition you can write this equation: N1 plus m1g, forces acting downward, should be equal to N2, forces acting upward. Then only the sphere will be in equilibrium. So this is the FBD for the sphere. Similarly, suppose in the same situation we have a third sphere kept again symmetrically but on the top of the Planck, like this. And now you have to draw the FBD of Planck. This mass M2, M1, M1, M3. Now draw the FBD of the sphere, or of the Planck. Draw the FBD of the Planck on your own. Get started with this and pull yourself up. Get started. Draw the FBD of the Planck on a piece of paper, please. Okay, the FBD should be something like this. mg acting downward from the center. There will be normal reaction at this contact and the sphere is kept above the Planck. The sphere would be pressing it downward and the normal reaction on the Planck would be downward. So this is the normal reaction. Let's call it N2 by the mass M2. And from here the Planck is pressing these two spheres downward, so the sphere would be pushing the Planck upward. So the normal reaction at these two contacts would be in upward direction. So this is the FBD of the Planck. Similarly, you can draw the FBD of the spheres as well. For the sphere, there are only two contacts, from the surface and from the Planck. So there will be two normal reactions. One will be mg downward. At this point, the normal reaction will be downward because the Planck is pressing it downward. So N3 would be downward. And from this surface, the normal reaction will be upward. So this normal reaction is upward. Now N3 is the normal reaction by the Planck, and in the Planck, N1 is the normal reaction by the sphere. N3 and N1 are action-reaction pair. N3 I have shown the normal reaction from the Planck on the sphere. N1 I have shown the normal reaction from the sphere on the Planck. Now these two are action-reaction pair. N1 will be equal to N3. So later on, when we write the equation for equilibrium, we have to understand that we don't have one extra variable. Actually, N1 is equal to N3. Okay.